Well, it's day 10. What have we got? Hi, and welcome to another episode. What we've got here is the PiHut Advent Calendar. Let it glow. We're on day 10. So let's find out what we've got. A little bit of a secret. I've already filmed this little bit. Made a mistake. So I've started again. So please ignore. You'll realize what it is. But anyway, let's open it up. Ta-da! As you can see, I've already opened it up. I didn't take it out, I just realised something and had to start recording again. We have some blobs of glue on a bit of wire. I'm assuming they're LEDs. So let's move across as we always do to the website. Let's make sure it's unplugged before we start ripping wires out and putting new ones in. We're on day 10, obviously. Let it glow advent calendar. Let's move the mouse around and move it up. It's another blinky day today. And what with the festive blink today's box brings us, it's a little black box you will find an addressable RGB LED dot strand. Very good. Another format of RGB LED offering us new ways to play. So far we've received RGB, diffused LEDs, and RGB ring, and now it's the ultra blinky RGB strand lights. This means you already have the knowledge to create programs for these lights, but we'll show you some new examples to give you more ways to play. Whoa! Warning! Some of today's activities contain fast flashing lights which may not be suitable for those with photosensitive epilepsy. And before we get going, let's have a little notice of how far away that little scrolly bar is. So there's a fair bit on today. Contents, as we know, LED adjustable RGB dot strand. Today's activities. Today we're going to show you how to wire up your dot strand and adjust your existing RGB LED code examples to make them work with it. We'll also give you some new examples using some of your components and a few real life project ideas. Fair enough. Before we get started, let's have a quick intro into our new favourite format of RGB LEDs. Every day it's a new favourite format. These dot strands work in the exact same way as the LED ring from day number 8, just in a different format. Inside those little white blobs are the same style of adjustable LEDs that your code can control. They just come in a much more flexible format for embedding into your own projects and decorations. The custom strands in your box have just 3 wires, 5 volt, data in, and ground. No D out pin, which is data out pin. I should have said that in full, since they said the other ones in full. And are fitted with jumper wire ends to make them ideal for breadboard prototyping. Construct the circuit. As always, make sure the Pico is disconnected from a USB cable when working on the circuit. Not so much the RGB cable, it's not plugged into your computer. Right, prepare the bed bin. Let's start afresh again. Remove all the components and wires, leaving just the Pico on the breadboard. Okay, if we must. Take that off, take all the wires off. I bet we end up putting someone back in the same space. I bet we do. I bet we do. Right, lots of wires, thermostat thingy out of the way. Right. Now we need to look at close-up of the wires and find some dots. Oh, there's some dots that very, 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 very faint. And when you find them, let's make sure they're on the left-hand side, it seems. Important, the very first thing we need to do is find the striped wire. One of the wires has dashes along it, and this is the 5 volt pin. You really need to make sure we get the wiring of this pin right. I wish they would say correct. Get this pin correct. When you're talking about left and right all the time, always use the the wiring of this pin correct, or will cause problems. So please get it right. You'll see it. I'm going to try to zoom in on the camera, but it's very, very faint. I understand why it's faint, because you don't want to sort of like draw too much attention to it, because it's not. They can't just do it at one end, it's all the way along the wire. See, there's those little says striped, but it actually kind of looks more dotted because it's not all the way around. But anyway, there's one wire that's got little black stripes on it. We shall call them stripes because that's what they call them, but that's there. So let's zoom back out again then, if we can. There we go. Dum-de-dum-de-dum. Right. Put the striped 5-volt pin into your breadboard on the left side, then fit the other 2 pins in order. They're stuck together. Next to it will be a space in between. See the image below. What does that even mean? They're not stuck together, they were separated already. I think the meant to separate the wires. Oh, so here we go. This is how it's done on the breadboard. So the striped one, we want that in 1, 2, 3, 4, 5. We want that in A5. Then we want to leave A4 alone, put the middle wire into A3, and the right one, see, the right one on A1. We've got that done now. So left, right, blah, 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 blah. We have lots of spare jumper wires now, so let's use them. Connect the left striped pin to the V bus physical pin 40. Okay, let's have a look. Okay, let's use a red wire then. Is that a red wire? I think it's a red wire. Looks like a red wire. On E5 on the top board, I'm going to take that down as it said physical pin 40, but for us that's actually J1 on the bottom board. Then we want a green wire, and we want to go from E3 across to A4 on the lower board. We've got a black wire, we've not got a black wire, we'll use a grey one. We'll use E1 on the top board and stick that in the pin next to the green one, which is A3 on the lower board. Okay, let's just make sure we've got that right. Yep, middle pin goes to the GPIO2, physical pin 4, and the right pin goes to ground on physical pin 3. That's what we've done. Fit this slide potentiometer. This slide is just too much fun not to bring back to the party, and it's a great partner for our dot strand. So let's get it back on the breadboard. We're fitting it in exactly the same place as day 7. Okay. So if you remember correctly, that's the 2 pins at the top, or the 2 legs, on the bottom. Let's make sure we've got that correct. So the 2 legs we want to go into, where was it? J30 and J28 of the top board, and that should bring us down to, where should that bring us down to? F30 on the lower board. There we go. Now we need a couple of wires again. Red one, where does it say it needs to go? Connect the, oh, it's saying connect the lower one first. Okay, fine. Get another grey wire then. And we need to take it from J30. Let's do it this way, J30. Across to, where are we? That's 10, 11, 12, 13. So 13, J13 on the lower board. Now top left leg, to the red wire, that goes from F30 to How's it going? Five. Yep. J5 on the lower board. And we get a blue wire from the, where are we? F28 all the way down to J7 on the lower board, the bottom board. That should be all correct now. Move the slider to somewhere interesting. Right, anything else? No, it should look like this. So let's move these LEDs around a little bit so we can see them on the screen here, on the camera. Well, you can see most of them. Oh, there we go, we can see all of them now. You could wire this dot strand straight into the breadboard holes next to the Pico 5 volts ground and GPIO pins are all close together enough. However, this adds some risk to wiring things up incorrectly as it's not clear and visible. Okay, so we're just making it easier for ourselves to be up over there instead of here and dragging, which wire was it? This one over to here and everything. It'd be a bit tight, but also just makes it easier to keep an eye on. Right. Simple strand test for activity number 1. You already know your stuff when it comes to controlling RGB LEDs. Do we? Did we forget stuff yesterday? Have we maybe got some sleep? Point is, we are learning. So let's run a quick test to make sure that everything's wired correctly and running as it should. As you'd expect, we've imported the nanopixel library, set our dot strand pin up as GPIO2 and set the number of LEDs to 15. When that shows red when we then show red at low brightness, 50,0,0 for 10 seconds, enough time to check everything is working. Copy the code over to Sonnet and give it a try. Right, so now, as we learned yesterday, they don't bother to tell us anymore to plug it in again, so let's plug it in. Always the second go when you're doing USB. Copy. No, we don't copy, do it. We press the stop button to make sure it finds it. We copy this across. We press paste. Right. As you'd expected, we've imported the nanopixel library. Set our dot strand pin. Okay. So we'll just press play, don't we? Or press run. There we go. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Is that how many it said? Yes, we've got 15. Ooh. And they all lit up. So great. There's no bust LEDs. Reusing and improving the LED ring programs. This is activity number 2. The cool thing about our adjustable ring and strand is that they work in the same way as and are both RGB. This means you can reuse any example programs and anything you come up with yourself just by setting the pin reference and number of LEDs. Take our bouncing lights program from day 8, for example. All we need to do is set this line to GPIO2 and 15 LEDs to adjust the strand. However, that's it's the strand equals number 2, 15, right? However, we would also need to change any reference to 12 LEDs throughout the code too, because our strand has 15. Our bouncing lights code could have been better if we used variables for a number of LEDs, meaning changing this once would fix it everywhere each time we use the new type of RGB. See, this is where variables start to become very handy, because you set them once at the beginning of your program, and then you go, oh, that should be a different value throughout the whole program. You don't have to carry on looking for that same bit. So Let's improve our code and make it reusable. We're going to make a variable called LED count, which is set to 15, the number of LEDs in our strand. Then we change its set line for the range functions to use the variable instead of the fixed number, meaning we only have to change the value to update our entire program, which is really handy when the programs grow bigger and bigger. Exactly. Couldn't have said it better myself. Right. We'll also do this for the GPIO pin number using a variable GPIO number, just to make things more user-friendly when we return the old code, when we return to old code later on. Lastly, we've created a variable called myColor. We can change this to whatever RGB code we like, and it will update our program where we've used it to. With that change, run the updated program below, and you now have a bouncing light across your strand. Okay. So let's do what we were doing yesterday, just getting rid of it and starting a new one. Paste. So let's have a quick look at the code. GPIO equals 2, LED counts 15, my color is 255, 0, 0. So that should be full on red, that shouldn't it? What I was going to say, yeah, this, as I said to you at the very beginning of some days ago, this is what's known as initializing, and it's very important you do this. And I still think they should have one of the color set to 0 when it gets going, so that if there's any LEDs turned on, they turn off. It's something I would personally put into the code if I was doing this. Right, so we've got stuff going on. There we go. Let's run it. Oh, so it's going all the way across and all the way back again. Very nice. Range start and stop step. Let's try something more advanced with the range function. So far we've used the range function like this with the RGB color codes, which it has allowed us to fade an LED in and out. You know, so that it goes from, well, either not on all the way up to full brightness. However, you can add some arguments to these brackets to define the value start range and the value stop range, the step stuff. So basically we can have a start, so we could maybe start at, I don't know, 10, stop at, oh, in fact it's explaining it here anyway. So 0 being off, as we know, and 255 being the full brightness. So what we could do though is the start at 255, stop at 10, so it never goes fully off. It just gets low, but it's never going to turn fully off. And we're going to count backwards to it because we're going by -1. We could make judged steps if we wanted to. We could actually count back in -10, but we'll stick with -1. This starts the LED value at 255 max brightness, ends the value at 10 low brightness at the steps of -1 to make it run down from 255 to 10. So straight to 20. I think that might be a typo. Anyway, so I think that should go down to 10. No way they've got that. Anyway, we've made an example program using exactly that. Our strand starts off with a low intensity red 10 and jumps to the while. The while loop contains the for loop, it runs through the each LED index. We immediately then move on to the nested loop that sets the red intensity for each of these looped LEDs from 255 finding the way original down to 10. Exactly, so there's a typo up here, that should be 10. To give this effect of constantly dim the red strand with a bright red light pulsing through it, have a go of the example below and read the comments to understand what each part is doing. Okay. Close that down, start a new one, copy the code. As I say, as always, type it out, you'll learn more. So let's look at the what did it say? Yeah, the comments. So obviously importing stuff, LED details, find the strand pin number and LEDs of the variable, that makes sense. LED index, we could mess about and make that already, count that way, but we're doing it this way for now. Different strand, iterate over each LED, fade in and out, iterated LED, use I value for the R in the RGB, fast delay, so it's not lasting long at all, the delay. Let's press play. So we've got it pulsing going down the LEDs, so they've all turned on and they're pulsing around. Good. We'll stop that for now. Or pulse with a different color. You could add a couple of lines to the bottom of the program to make a different color pulse through the red strand. First, change the nested loop for the pulse to use a different color. We wanted to try white, so we've set the RGB color to use I in all three variables. Yes, you can do that. Of course you can. It's a variable. You can stick it anywhere. Then after the nested loop ends, we can set the color of that iterated LED back to the original low intensity red. Give it a try. Okay. Press play. So now it's pulsing white as it bounces around. That looks cool as well. Stop. Static odds and evens. We've created a classic old school festive red and green pattern with our dot strand by telling our code to fish out the odd and the even LED numbers in our index for the use. To do this, we use a modulo operator. Sounds like a bad 90s rock band. It sort of does. Let's explain what it is. A modulo operator in MicroPython, the modulo operator is a percent symbol. Oh, right. When we use this in our code, it can give us the remainder of the division between two numbers. For example, we know 12 divided by 5 is 2.4. We want to know how many times we can get 5 into 12 and what's left afterwards. So what's the remainder? Yeah, as it says over here. We can get 5 2 times from 12 and leaves us with 2 left over, the remainder. We could use modulo to find the remainder for us like this. We pop this into the shell. Okay, so we'll just copy that because we don't want to copy the answer. That wouldn't work very well. Right, so we paste it and we should get 2, which is fine. Okay, but how does the modulo operator help with LED strands? We can use the modulo operator to tell us the number is divisible by 2. All even numbers are divisible by 2. And we'll leave a 0 as remainder. So this test will tell us if a number is even. We can tell our code to look the LED index on our list and tell us if the divisible by 2 is the remainder 0. We can use this if statement to say do this if it's even or do this if not. The code example below includes a list of LED indexes along with the usual lines. We don't need a while loop here as we're just showing static colors. Instead, we will use a for loop to iterate over each LED in our index. Inside that for loop is an if statement and an else statement. The if statement says for each LED index we initiate over, we divide it by 2, is the remainder 0. If it is, this means the number is even, and we'll light those with even LEDs with red. An else statement grabs everything that isn't even, odd numbers, and lights them green. Simple, right? Try the code below and see for yourself. Okay. There's probably a few different ways to solve this problem, but this is the way that they're doing it. So if we go, so LED divided by 2 is equal to Now, I don't know about you, but it must say something about this. Has this copied the code in properly? Yes, it has. Because in the real world, 0 divided by anything is error. And here we go. So it must ignore that and class it as an even number. And there we go. Red and green. Activity number 5, flashing odds and evens. We can make the example above more snazzy by altering the odd and even LEDs between red and green. Equally as old school, just a little bit more fun. We don't have to change a lot of this to achieve this, but we simply need to put our for loops inside a while loop, add a second loop to do the opposite colours to the first one, add a delay between each loop. None of this is new to you, it's just another loop after the first one, so check out the example below and code commentary, then give it a try. Okay. Right, so we've got all the normal stuff up here of sorting out what pins what colours what the LED index is. A bit of a sleep in between. So first loop runs red evens and green odds. Okay. Delay for a second, well, half a second actually, and then blah 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 blah. Do it the other way around. This is why it makes sense about having the red and green already set up, because we now can just, we don't try to remember numbers. We're not Photoshop. We're not remembering it off the top of our head. I know some people do, but not everybody. And blah blah blah. Doing it, and then it's going to run and repeat, isn't it? So let's run that. So flashy flash now. That does look cool. Very nice colours actually. They're actually very nice LEDs. It's a shame there isn't a huge strip of it that could stick it around the fireplace for Christmas and have a really ugly breadboard just stuck in the but that's the thing, isn't it? We could do this sort of stuff now. I wonder how many LEDs you can stick on. Is it more than 15? Could you buy a longer strip of say 30? Now on to activity number 6. Let's stop this code so it's a bit not so distracting. Right. Activity number 6, strand slider. Let's bring our slide potentiometer back into the code and use it to run a fun program with our dot strand. With our LED ring, we use the slider to fade the LEDs and control the speed of flashes, but we think it would be fun to slide the LEDs to light up and down the strand. Okay. To do this, we need to get into the maths again, splitting the analog range up and across the numbers of the LEDs, and let's do it. Code breakdown. We'll of course need to make sure we'll import the ADC again, as well as setting the right ADC pin up on the slider, as we did before, GPIO 28. Now we want the slider with a range of 0 to 65,535 to drive our LEDs, which we have 15 of, so we need to convert the analog range to the LED range. In our setup, we use the following line to divide the analog range 65,535 by the number of LEDs, which is 15, giving us a variable LED division that we can use to divide our reading by. So that's the code that does that bit. Our while loop then takes the analog reading from the slider, which then divides by the LED division variable, giving almost an LED number we can use in our code. However, we need to be a round number, so we use the round function on this at the same time. We decided to do this all in one line this time, rather than taking a reading separately, then manipulating the value. We spaced it out to make it easy to read. MicroPython doesn't care. Okay, so we've got the reading, then we're looking for the round number. Remember, we're rounding up or round, we've got the potentiometer reading all by itself there, divided by the light division. So okay. So, however, does this work? Here's a working example. 65,535 divided by 15 equaling 4,369. So roughly every 4,369 of analog range we give us 1 to light one of our LEDs. We take the reading from the slider, which is between 0 and 65,535. Let's say the reading is 15,000. We divide that number by the 4,369 we got earlier, which equals 3.43. We round that 3.43, giving us 3. So yes, it rounds down. It either rounds up or it rounds down, depending on that whole 0.5 thing that I told you before. Right. We then tell our code to light up that many LEDs. We use two for loops to set which LEDs should be on and which should be off, and we need our code to turn the LEDs off again when we slide it back down. The first loop is straightforward. It uses the values from the calculation above the range, and we turn these LEDs on with the color. So yeah, that makes sense. So that's going to be full blue because it's RGB. So that's going to be full on blue, right? The second fold uses the start-stop step options we covered earlier to help it identify all the LEDs that should be off. We use the reading as a start value and the LED count as the stop value with a step of 1. This gives us all the LEDs that shouldn't be on. Okay. This could do with a few read-throughs, couldn't it? All that's left to do is write the LED strip after both of the for loops have set the LEDs to be lit, with a short delay to ensure smooth motion with the LEDs when we slide. The full program is below. Give it a go. Okay, so get rid of that. Copy the code. Start a new one up. Press paste and run it. So we've got blue fully off. 1, 2, 3, 4, 5, 6, 7, 8. 8 is a bit blinky. That's in the center there. You just push it just at the best. Bit flaky that because there's that little catchy bit in the middle. Can we see that by the way? Is it in there? Yeah. Keep going. Keep going, keep going. And the last one, there we go. Hey, can I be a raven now? What? No, maybe not. Let's turn them all off. Right, stop. Move on to the next bit. And using random makes everything more fun. We can tweak our example above to fill the strand with random colors instead of the fixed blue value, because random function is the best thing ever when it comes to LEDs. It creates a great effect because it's constantly looping with a 0.1 second time delay, meaning you get to slide the LEDs whilst they twinkle lots of different colors when lit. All we need to do is import random, borrow the random RGB color code we use from day 7, activity number 4, pop that into our while loop, then set the first for loop to use the RGB variables of the LED color. Okay. Copy the code, paste. So let's see, so all everything's set up, we initialize that. We're getting the 65,535 divided by the LED count, which in our case happens to be 15. Reading the potentiometer, rounding that around so that it makes an integer, a full number, no decimal points. Rounds up or rounds down depending. We've got RGB set up as being a random number. Stick in the RGB colors, and if they should be off, they're off. And 0.1 of a second delay. So we'll press run, and it will look like nothing is happening because I left the slider down at the bottom. So let's go again. I've got them all going. Because they're going so fast, they're going a bit white. So what I'm actually going to do, I'm going to slow that down to 5, half a second each time. I'll press play again. There we go, we get to watch the colours blinking around. I know I wanted like twinkly, but it was happening so fast it sort of looked like they were stuck at white. Oh. Right, that works. We'll stop it though. And that's day 10 complete. Oh, it actually says something here. If that activity was a bit too bright for you, just drop the maximum intensity range from random value to low value such as 50. For example, random 50. Okay, let's go back and do that then. We can change them all to 50. Oops. Let's try running that again. It's not as bright this time, but we can control though on how many we want to actually be done. I know this is just an example, but I can't really think of where you would want to do this. So if you've got, I've got a whole ship of LEDs, but I only want 3 lit. But the point is, it shows you how the code works and how you can do fancy calculations to do different things. Because now you know how to do that kind of calculation, you can apply it to something else. It doesn't have to be LEDs. It might actually really come in handy for something. The point is though, that's what we've learnt today. I'm not going to read day 10 complete because there's a lot to that as itself. So, what can I say? That's definitely been interesting to play around with that. I feel like we're getting some coding to really get our teeth into now. At the very beginning it was a little bit basic, but everyone's got to start somewhere. I'm not knocking it. It's better to start at the very beginning and work your way up because you'll understand it better instead of going, oh, this all looks very complicated. It's too much for my little brain. I'm going to stop. Start at the beginning. Get yourself through it. It becomes easier and easier every time you do a bit more of it and learn a bit more. I realise I'm going through it a bit too fast, but I'm trying to show how interesting this can actually get. Maybe the first few days were a little bit boring for some people, but by the end of it, it's going to be some quite interesting code, I think. So we've got 2 days left, which means get yourself down to the comments, say some things, nice things I hope. Don't forget to have a look in the description for the Discord and the Patreon links. Don't forget to hit that like button, the subscribe button, and that notification bell because it's so important that people keep coming back. Tell your friends, tell your family you want one of these just in time for Christmas and get them to have a look at it and know why you want one. But as always, happy gaming.